Now let us consider collisions. What is a collision? A collision is defined as interaction between two bodies with or without physical contact which may result in change in momentum. So it is said to be an interaction between two bodies with or without physical contact which may result in change in momentum. The momentum of the body changes even without any physical contact. That kind of interaction is what we call a collision. So normally with contact, day-to-day life we will observe a bus in motion collides a body at rest. So this is a collision. Here there is a physical contact. Because of this, the momentum of the bus as well as the body changes. A ball is projected onto the wall. So afterwards it bounces. It's a collision with a physical contact. Then where we will observe this without contact. So normally without contact, nuclear and atomic collisions. Nuclear and atomic collisions in that there is no need of any physical contact. Suppose when a body is under the influence of the electric or magnetic fields, the momentum of the body may change. For example, an alpha particle starts moving towards a nucleus. Stationary nucleus means it has a positive charge. Alpha has positive charge. As the alpha is approaching, it may deviate from its path. Here, without any physical contact, the momentum of the body's alpha particle is changing. It's also a collision. So, in atomic and nuclear collisions, there won't be any physical contact between the bodies, but still the momentum of the bodies changes. This is also a collision. So, an interaction between two bodies with or without physical contact which may result in change in momentum. These are physical contact collisions. This is an interaction without any physical contact. Now, it was observed that collisions are basically divided into two types: elastic and inelastic. What is this elastic collision? A collision in which both momentum and kinetic energy are conserved. For the participating bodies, the total momentum as well as total kinetic energy must be conserved. Number 1, momentum conserved. Number 2, kinetic energy conserved. If both the things are conserved, then the collision is said to be elastic. Inelastic, only momentum is conserved. Momentum is conserved, no kinetic energy conservation. Now let us take a body of mass m1 is moving with velocity u1. It strikes another body of mass m2 moving with velocity u2, say in the same direction. Here u1 is greater than u2. We know that if u1 is greater than u2, after some time they collide with each other. Now after collision, let us say m1 moves with velocity v1 whereas m2 moves with velocity v2. So this is before collision, this is at the time of collision, this is after collision. Now if I consider law of conservation of momentum, law of conservation of momentum. So what it suggests? We know that according to law of conservation of momentum, the total momentum before collision must always be equal to total momentum after collision. So m1 u1 plus m2 u2 must be equal to m1 v1 plus m2 v2. This is called law of conservation of momentum. Total momentum before, first body m1 u1, second body m2 u2. After moment collision, m1 v1, m2 v2. Consider law of conservation of kinetic energy. So according to this, total kinetic energy before, half m1 u1 square for first body, half m2 u2 square for second body. This must be equal to total kinetic energy after collision, half m2 v2 square. So momentum conservation, kinetic energy conservation. If both are conserved, first and second equations are obeyed by any collision, then the collision is said to be elastic. So elastic, both are conserved, momentum and kinetic energy. Equation 1 and equation 2 both are valid. But inelastic, only equation 1 is applicable and not equation 2. Now, what are the examples for these elastic collisions? Because here kinetic energy and momentum both must be conserved. So, normally all visible collisions are considered to be inelastic. All visible collisions. A bus colliding a vehicle car, an aeroplane hitting a ground, a ball projected onto the wall, all these cases, these are all visible collisions you can see with your eyes. So they are all inelastic collisions. But if I consider perfect elastic collision, not possible. There is no perfect elastic collision in nature. All collisions are inelastic only. But for practical purposes, collision between two billiard balls. Collision between two billiard balls is considered to be elastic. Similarly, atomic and nuclear collisions. We can also take atomic and nuclear collisions as elastic collisions. So all visible collisions in nature are inelastic, but for practical purposes, billiard balls collision and atomic and nuclear collisions are considered to be elastic, and there is no 100% elastic collision in nature. Impossible to have 100% elastic collision. So elastic collision, momentum is conserved, kinetic energy is conserved. Inelastic, only momentum is conserved. But if I take any collision, total energy is always conserved. Total energy is conserved in both the collisions, whether it is elastic or inelastic. Total energy is always conserved. If kinetic energy is conserved, it is elastic. Kinetic energy not conserved, it is inelastic. For example, if I take inelastic collision, a ball is projected onto the wall. It strikes the wall, returns. Now if you observe, when the ball hits the wall, you can hear sound. Sound is produced. At the point of contact, if you touch this surface, after collision, just to touch this part, if you touch this one, you can feel a rise in temperature. So heat is produced, and there is a possibility for a shape change, deformation. After hitting the wall, when it comes back, you can notice there is a deformation possibility. So this is called elastic energy. That means normally in a collision, the energy of the total kinetic energy of before collision is converted into sound energy, heat energy, elastic energy, etc. But if I take the total energy, that always remains constant. That means the sum of kinetic energy, sound energy, heat energy, elastic energy is always constant. So we know that energy conservation must be applicable for any kind of bodies in nature. So here also total energy is conserved. Now let us consider one-dimensional elastic collision. One-dimensional head-on elastic collision. Here head-on, so centers on the same line. Imagine the two bodies are moving with velocities u1 and u2. This is m1, this is m2. They collide with each other. If I imagine u1 is greater than u2, so final velocities, m1 moves with velocity v1 and m2 moves with velocity v2. Generally v1 will be less than v2. Before collision u1 is more, and after collision v2 is more and v1 will be less. If I use this as elastic collision, so I must apply conservation of momentum as well as conservation of energy. m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Equation 1, equation 2. If I solve these two, I can prove that the final velocity of the first body after collision m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. Similarly, for second body, bring this term this side. Since it is first term, it is 2m1. So take this term to that side, but reverse this. It is m2 minus m1 by m1 plus m2 into u2. These are final velocities in the case of one-dimensional elastic collision. Here both the bodies are moving along the same direction. Final velocity of the first body m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. This is second body 2m1 by m1 plus m2 into u1 plus m2 minus m1 by m1 plus m2 into u2. Now let us consider, say, case 1. Moving in opposite direction, bodies are approaching each other. So instead of considering both are moving in the same direction, let us say m2 is approaching. Now here I can use the same equations, only u1 place plus u1 but u2 minus u2. Since the direction is reversed, take it with minus sign. Use the same equations but replace u1 positive u1, so remains same, but u2 minus u2. That gives the final velocities. Now suppose masses are equal. Let us assume the two bodies have identical masses. Then what about v1? Collision between two identical bodies. Elastic collision between two identical bodies. Then v1. Now if I take this equation, m1 and m2 are equal. So when I say m1 and m2 are equal, this term becomes 0. Here m1 and m2 equal, so this is 2m2, this is 2m2 gets cancelled, so it becomes v2. And v2 is, now this equation, here m2 minus m1, these two terms, this is same. So when I say these two are equal, these two gets cancelled, so this term is 0, and here m2 place, put it as m1, 2m1 by 2m1 into u1, so v2 becomes equal to u1. That means first body will gain the velocity of the second one, whereas second body will gain the velocity of the first one. So this is what we call exchange of velocities. Exchange of velocities. So when elastic collision takes place between two identical bodies, after collision they exchange their velocities. First body will gain the velocity of the second one, whereas the second body will gain the velocity of the first one. Now suppose if I take case 3. Imagine a heavier body in motion, m1, m2. Second body is at rest, first body is in motion. Here m1 much greater than m2 collides a lighter body at rest elastically. Then what about the velocity of the first one? Now let us take the same equations. Here second body is at rest, so need not consider this term. Now coming to this case, m1 is much greater than m2, so m1 minus m2 can be written as m1, m1 plus m2 is also m1. So this becomes equal to actually m1 plus m1 minus m2 by m1 plus m2 into u1, but here m1 is much greater than m2, therefore I can say it is m1 by m1 into u1. So m1 and m1 gets cancelled. v1 is equal to u1. Then what about v2? Now same equation, but u2 term 0. So take this part. Two m1 by m1 plus m2 into u1. But m1 is much greater than m2. That means 2m1 by m1 into u1. So I can cancel m1 and m1. So this becomes equal to 2u1. So the meaning of this one, when a heavier body collides, lighter body at rest. Conclusion: v1 is u1. Here this is remains same. That means heavier body continues to move with the same speed, and lighter body, it was originally at rest, but v2, the lighter body is second velocity, it is 2u1, moves with double the speed of first one. So when a heavy body in motion collides a light body at rest elastically, heavy body, its velocity is not going to change, it continues to move with the same speed, but lighter body moves with double the speed of the first one. The first one moves with 10 meter per second, now this one moves with 20 meter per second. Now take case 4, reverse case. A lighter body in motion collides a heavy body at rest elastically. So here lighter body is m1 moving with the velocity, collides the heavy body at rest. We know that first body equation, m1 minus m2 by m1 plus m2 into u1. Anyhow u2 term 0, no need to consider. Here m1 much negligible compared to m2, so I can neglect this term, so this becomes u1. That means lighter body moves back with same speed minus u1. Originally it is u1, now it is minus u1. That means the lighter one moves back with speed u1. Now what about heavier body? v2. Since u2 term is 0, it is 2m1 by m1 plus m2 into u1. Here m1 very small compared to m2. So once I say m1 is very small, so here I can write as, if I take m1 common, 1 plus m2 by m1 into u1. So here m1 and m1 gets cancelled, so remaining 2 by 1 plus m2 by m1 into u1. This m2 by m1, very large term. Therefore v2 almost rest 0. That means heavier body continues to be at rest. So lighter body moves back with the same speed, but heavier body continues to be at rest.